Hi everyone, so today we're going to talk about maximum power transfer, and by the end of the session you should be able to derive the conditions for maximum power transfer in the circuit, and you should be able to describe the difference between maximum power transfer and efficiency, and that's something that is confused a lot, so pay attention to what the difference is. So let's talk about power in Thevenin equivalent circuits in general. If we look at the example we used before with our 10 volt and 12 volt source, if I want to form a Thevenin equivalent to represent the circuit connected to the load, I could remove the load and then find the equivalent circuit, which we did before, which is here. Now, if I look at the power dissipated in this Thevenin equivalent circuit as compared to this circuit, I'll see it's quite different, even though they are supposed to be the same thing. So if I look here, 10 volts and 12 volts, it means the voltage across here is 2 volts, and then I have 10 ohm resistance, so I know P is equal to V squared on R, which will be 4 on 10 is 0.4 watts. That is 0.4 watts when there's nothing connected between the terminals. If I go to this circuit now though, and there's nothing connected between the terminals, then the power dissipation is 0 because no current flows in the circuit. So while these are supposed to represent the same circuits, we see that they actually have different power dissipations. In fact, the only thing that remains the same for the Thevenin equivalent is what happens between these nodes. So the Thevenin equivalent makes only what is in between these nodes here the same. So that is, the power dissipated here is 0 because the current is 0, so I squared R will be 0. And the same holds for here. There's no current here, so the I squared R is 0. So the Thevenin equivalent, remember, preserves the voltage across and current through the terminal component, and that is the only thing that remains the same. So even though we say it is an equivalent for the circuit, it is only equivalent at the terminals. Now, since the terminals are equivalent, the power in the terminals are equivalent, and we could actually derive what is the condition for maximum power being transferred to the terminal component using a Thevenin equivalent circuit. So, as we said before, and the maximum power transfer, if I wanted to find it for the power going to the load resistor, I have to simply find an expression for the power in the load. So the power in the load, I can first find the voltage using my voltage divider equation, and then I know power is V squared on R, so V load squared on RL, which is the load resistance. So if I substitute this equation into here, I should get this. And then to find what is the maximum power, if I want to find what is the maximum power possible with respect to the load resistance, then as with any finding any maximum point, I have to find the derivative and the point at which the derivative is 0. So I differentiate the equation, and I should end up with this. You could do that at home using your quotient rule or your product rule. And once I have that, I could see that if I set this equal to 0, that occurs when RTH is equal to RL. So the maximum power transfer occurs when R Thevenin is equal to R load. And this is why you'll see things like impedance matching. If you ever try to work with a stereo system or any speakers of any sort, you would see they're matching. They always talk about matching the impedances, and you'll see the speaker might be a 3 ohm speaker or an 8 ohm speaker. essentially you're looking there at the Thevenin equivalent resistance. So by matching the speaker, you could get the impedance of the speaker, you could get the most power across. So that is the simple thing for maximum power transfer. If you need to find what is the maximum power that could be transferred to any two terminals in a circuit, you have to find the Thevenin equivalent looking into that circuit, and then the load you attach must be equal to the Thevenin equivalent resistance, and that will give you the maximum amount of power possible. Now this is often confused with efficiency. Usually people think if I could get the most power out, then that means it's the most efficient, but that's not really true. In fact, at maximum power you don't have a very high efficiency, and we'll see how that works. Remember, the efficiency, or eta, is equal to the power out over the power in. So this is the equation we are going to look at to calculate the efficiency, and we're going to compare that with the maximum power for all these different values. So we know that for maximum power we should have 2.5 ohms here. So what we'll do is do a sweep of these resistances going from 0 all the way up to 100 ohms, and we should see that at 2.5, which is here, it should peak. The maximum power should peak, but when would the efficiency peak? That is the question. So you could plot this in Excel, or you could plot it in MATLAB and see what you get. So you could go ahead and pause the video and try to plot it, or plot at least some of them by hand. It's not that difficult. So if we want to look at the equations, the power through here, we could find the current first, I, and I will be equal to 11, which is the voltage, over 2.5 plus RL. And then we know the power transferred to RL, PRL, is equal to I squared RL. And that will give me the power transferred. And if I want to find the efficiency, then the efficiency would be equal to the power transferred to the load, which is PRL, over the input power, which is 11I. P is equal to VI. So we could use those two equations and we could find out the efficiency and the maximum power. Good. So if you've done that, you should hopefully get something like this. And you'll see at 2.5, which is 2.5 ohms, we have the maximum power, which is 12.1 watts. And for the efficiency at 2.5 ohms, we have just an efficiency of 0.5, or 50% efficiency. And the efficiency just keeps going up. So the larger the load resistance, the larger the efficiency. And that makes sense when you think about it, because the larger this resistance is, so if it is, say, even 100 kilo ohms, it means if I look at my voltage divider, V is equal to VRL is equal to V source multiplied by RL on RL plus R Thevenin. That as RL becomes very large compared to R Thevenin, then the ratio goes to 1. In other words, more voltage drops across RL. And because a greater percentage of the voltage is dropping across RL, it means a greater percentage of the power will be across RL. So will be dissipated in RL, sorry. Whereas for the efficiency at 2.5, which is the matched impedance, we have the maximum power. Below that it is less, and above that it is less. So the maximum power occurs when we have 2.5 ohms here, and we can see the same resistance. It means the same voltage drop, so half of the power. So we have half efficiency, 50% efficient. So I hope you could understand now what is the difference between maximum power and efficiency. So to summarize, by now you should be able to derive the condition for maximum power transfer, and you should be able to describe the difference between maximum power transfer and efficiency.